All right, my name is David Malan, and I indeed teach a class called CS50, an Introduction to the Intellectual Enterprises of Computer Science and the Art of Programming. In 1995, I was a first year here in Matthews Hall in the corner of Harvard Yard. This was the room that I myself lived in and Matt Damon a few years prior. But it was in this room that I came up with this really long, exhaustive, precise list of like the 32 courses my first year that I planned to take for the next 4 years. And it was filled with ec and government, a bit of statistics and math. And funny enough, some years later, like most of what I ended up doing here was not on that original list. But rather, I gravitated, though, in that first month of school where you meet with your RA or your proctor one-on-one to talk about what classes you might be interested in, what you want to do in life. And I was so focused on things with which I was already familiar when I came into Harvard. I really liked history and constitutional law in high school. And so I kind of gravitated toward the familiar. And I filled my 32 courses preliminarily on this sheet of paper with those courses that seemed already in my orbit of comfort zone. But fast forward a few years later, and then even in grad school, like the most impactful, some of my most favorite classes that I took here ultimately were Dramatic Arts 101, Latin A, an Introduction to Archaeology, and a little class called CS50. Only in my sophomore year did I finally get up the nerve to come into CS50. I shopped it, so to speak, before even registering. I wanted to get a sense of what it was like. I probably followed some friends into the classroom, and I was not really sure it was for me. I definitely didn't think of myself as a computer person per se. From what I'd seen in high school, it just didn't look that interesting, typing away on a keyboard and programming or whatnot, at least as far as I'd seen friends doing so in high school. So it really was for me this field, this course to beware. But curiosity got the best of me. I only stayed in the class the next day because the professor let me enroll in it pass-fail, fearful as I was of an actual letter grade. But fast forward just a few months later, I switched my concentration or my major from government to computer science. And that exploration, that curiosity, that experimentation academically really changed my trajectory in life. And what I didn't realize at the time was that computer science wasn't programming. It really was all about just information, which of course is omnipresent. And it was really about problem solving. This just act of taking inputs, trying to get outputs, like solutions to problems, and somehow figuring out what's in that proverbial black box in the middle to make all of that work. But to do this, I realized pretty early on that you need a system for representing these inputs and outputs. No matter the human language you and I speak and communicate with, we all have to speak some common language. And as you probably know, even if you're not computer people yourselves, like what is the language that computers actually understand? The so-called binary system, bi meaning two, and you've probably generally heard that computers speak zeros and ones somehow. Well, how can that possibly be? Well, if they have zeros and ones as their only vocabulary, how do we get bigger numbers than 0 and 1, like 2 or 3? How do we get letters of an alphabet, be it English or something else, colors or sounds or video or anything else? Well, inside of a computer are these tiny little switches known as transistors. And of course, they've got a bit of memory where they can remember things as well. And if you turn these switches on, that's how a computer might remember a 1. And if you turn the switch off, thereby making it devoid of electricity, it's how a computer might represent the number 0. So if you have just one of these switches, which if I can steal a light bulb here from Sanders, if you have just one switch like this light bulb has here, if it's off, it might represent a 0. And if it's on, now it might represent a 1. Well, how do I count higher than 1 in binary? If I only have 0 off or 1 on, well, I need another switch. And in fact, maybe I'll grab just a couple of more of these. And to count even further, here's how I might therefore represent the number 1. If I want to count up to the number 2 or 3, you might think in our human world that you do this. 2, and then 3. And now if I want to count to 4 or 5, I of course need to go grab even more light bulbs. But not if you're a little bit clever about this. And in fact, computers don't need this many light bulbs to count up to 3 or to 64. We can count much more cleverly like this. For instance, if this is still the number 1 here on the rightmost end of these light bulbs, and I want to count to the number 2, well, let me be a little more clever and actually take into account not just how many light bulbs are on, but which ones are on. So let me propose that I turn this one off, but turn the middle one on, and I claim now this is the number 2. This is how a computer represents 2 by turning 2 light bulbs or switches off and just turning on the middle one. If the computer wants to represent 3, we turn this one back on. And so even though there's only 2 on, we're now representing 3. And if we want to represent 4, we go ahead and turn these 2 off. And we turn this one now on. And this is how a computer would represent the number 4. And I can keep doing this for 5 and 6 and 7. And beyond that, I might need another light bulb, but there's just a pattern going on here. And it turns out, even if that was a little bit cryptic and seemingly random, it's actually more familiar than you might think. Here, for instance, is now digitally what I just did in analog form with these actual lights. So 0, 0, 0 is like off, off, off. This, if we do out the math, is how a computer would represent the number you and I know as just 0. If a computer wants to count to 1, it turns on one of those switches, one of those light bulbs, the one all the way on the right like I just did. So this is how a computer would represent 1. Here's how a computer would represent 2, 3, 4, 5, 6, 7. And indeed, if I want to represent 8, what do I probably need to do? Like another 0 or 1, another light bulb to do this. But now this pattern may be perhaps non-obvious, but let me propose that we consider what you and I take for granted since grade school, just doing numbers more generally. Here, of course, is the number 123. But not really if we really go back to basics. This is just 3 symbols on the screen, a sort of straight line, a curly line, and a doubly curly line that you and I ascribe meaning to, 123. But think about what your grade school teacher probably taught you. The rightmost column of numbers is the ones place, or the ones column. Then you have the tens place, the hundreds place. And so the fact that these symbols are from left to right, 1, 2, 3, means you're doing some really quick mental math just natively nowadays, whereby it's 100 times 1 plus 10 times 2 plus 1 times 3, which of course is 100 plus 20 plus 3. Ergo, the number you and I immediately know is 123. Well, now let's take away the digits 2 through 9, which you and I take for granted in our decimal world, dec meaning 10, and just consider that these placeholders could very well just mean different things. So generically, if we've got 3 digits in our decimal world, they're the ones place, tens place, hundreds, thousands, 10,000s, and so forth. And that's because we're using powers of 10 in our human world. 10 to the 0 is 1, 10 to the 1 is 10, 10 to the 2 is 100, and so forth. So let's just change what that base is. And if we take away the digits 2 through 9, leaving us with just zeros and ones, that's OK. We can still count as high as we want, because now we have the ones place, 2 to the 0, the twos place, 2 to the 1, the fours place, 2 to the 2. And so why is this number here, the number you and I know in decimal, as 0? Well, it's 4 times 0 plus 2 times 0 plus 1 times 0, which is obviously 0 itself. Why is 0, 0, 1 the number you and I know as 1? 4 times 2 plus 4 times 0 plus 2 times 0 plus 1 times 1 gives us 1. And if we fast forward to whereby we might have, say, 0, 1, 0, 0, 1, 1, or let's go all the way to the end, 1, 1, 1, this is not 111 in this context of binary. This, of course, is the number 7, because it's 4 times 1 plus 2 times 1 plus 1 times 1. So there, even if you're not a computer person, never thought you would study or know much of anything about computer science, we all now know binary. We have this common language with which we can begin to solve problems by representing those inputs and representing those outputs. But numbers, of course, only take us so far. Like, what if we wanted to use not just 3, but like 8 bits. And 8 is a more common unit of measure in the computing world because it's just more useful to have more switches. This is a byte. Byte implying 8 bits. And a bit is just a binary digit, a 0 or 1. So here's the typical unit of measure, bytes. And from that, we get kilobytes, megabytes, terabytes nowadays, gigabytes, and more. Well, this pattern here, if we actually did out the math, that's like the 64s column. That's the ones column. So this is the decimal number 65. That's how a computer would represent 65. And it turns out, in the right context, that's how a computer represents the capital letter A. So we humans just need to decide, as our ancestors did some decades ago, what patterns of zeros and ones we're going to use to represent letters of the alphabet as well. There's this whole system called Unicode that standardizes not just English, but so many other human languages as well. And here's just an excerpt of like 128 possible mappings of just numbers in decimal in one column to the corresponding letters in the other. So let me highlight just the middle portion here. A is 65, B is 66, C is 67, dot, dot, dot. H is 72, I is 73. And there's an association between numbers and letters for every other symbol in English and now other human languages as well. So if you were to get a text message today or an email or anything digital that had these 3 bytes underneath the hood, somehow sent wirelessly to your device, this pattern from left to right, if we do out the same math as before with the ones place, twos place, and so forth, it's the numbers 72, 73, 33, if you just do out the math 3 times. Anyone have good recall and want to tell us what this says on the board? So it says hi. Why? Well, 72 was H, and 73 was I, and a little off to the side was 33, which was just an exclamation point. So this is how you would type in all caps hi to a friend in an email or a text message or the like. So let me just stipulate that there's so many other things we can represent, certainly whole words. And in fact, wouldn't it be funny if this whole time there were these 64 light bulbs on the stage representing something in Unicode from left to right in units of 8? Perhaps it might spell a little message. Feel free to take a picture if you'd like to do that homework later. But indeed, we can represent more than just numbers and letters. We can do a similar mapping between zeros and ones and things like colors as well. Things like music. And from there, we can get images and we can get videos. We all just have to agree on some convention for maintaining those associations there. So even these things too, which we're all too fond perhaps of sending nowadays in texts or emails, even these emoji too, this and hundreds of others are just patterns of zeros and ones that Google, Apple, Microsoft, and all of us have sort of agreed in just using computers today to use the same pattern of zeros and ones on one device and on another. But that, of course, is just the left and the right of this picture. How we might represent inputs and outputs, we all just use binary. And we maintain those kinds of mappings between letters and numbers and more. Let's take a look inside this black box and consider what it means to actually solve a problem in computing. Without even touching a keyboard or code, these things known as algorithms, step-by-step instructions for solving some problem. Now, nowadays, we're all in the habit of using things like your contacts on your iPhone or Android device. Those contacts are typically sorted alphabetically by first name or last name. This isn't all that different, honestly, from the technology we used in 1995 in Matthews Hall. When we wanted to call someone, we used the old school incarnation of this, a phone book. Same idea. Lots of names, lots of numbers, alphabetized from A through Z. So how might a computer go about searching via autocomplete or something like that? Or how might a human back in the day go about searching the same technology if you're looking for someone like Ron in the phone book, assuming we're searching by just first names? Well, we could go to the first page here and just start looking one page at a time from left to right. Is this Ron? Is this Ron? Is this Ron? Is this algorithm step-by-step correct? Well, I find Ron, if he's in this phone book, starting at the beginning, going, yeah, one page at a time. It's kind of stupidly slow because he's obviously going to be farther down in the phone book, but I'll find him eventually. Well, what about a different algorithm? 2 pages at a time. So 2, 4, 6, a little harder to do on the fly, but 2, 4, 6, 8, 10, 12, 14, 16, 18, and so forth. Is that algorithm correct? Looking for Ron 2 pages at a time. I'm seeing no. Why? Yeah, I might skip Ron because he sort of accidentally gets sandwiched between 2 of those pages. Now, I don't have to throw out the whole algorithm. I can still fly through the phone book twice as fast, and maybe I should just double back 1 if I go a little too far in the phone book. So it's recoverable. But generally, what I would do back in the day, and what your iPhone and Android phone and Mac and PC are doing, is they're generally just going roughly to the middle of that long list of names or this many pages. And you might look down and see, oh, I'm in the M section. So that's far too early in the phone book. So Ron's got to be this way. And the problem can then be divided and conquered, so to speak. And we can do this all too dramatically here, taking the phone book the easy way, down this way, taking the phone book, tearing it in half, and leaving us with a problem that's not like 1,000 pages now, but maybe 500 instead. And now I go here. I went to the T section. So I went a little too far. So I can, again, divide the problem in half, throw half of it away, leaving me with what, like 250 pages, then 125, then 67, give or take. And there's some rounding issues that, to be fair, we'll have to sort out. But so long as we handle rounding, eventually we'll find ourselves with Ron on or just not on this page at all. Now, of course, we can only do this once, but that's what's known as binary search. By, again, meaning 2, and dividing and conquering more familiarly, whereby we're just dividing the problem in half and half and half and solving it so much more quickly. How quickly? Well, if it was 1,000 pages to begin with, that first algorithm might have taken me like 1,000 steps. Slow to find Ron or Zacharias way at the end of the phone book. Second algorithm, maybe 500 steps because I'm going 2 at a time. But the third algorithm, how many times can you tear a phone book in half if it's roughly 1,000 pages? Some quick math. So roughly 10 times, only 10 times, and that's down from 500 in just that second case. And so what you learn to leverage in computer science is ideas like this. If we plot this very simply, vertical axis here is the amount of time to solve a problem. Horizontal axis here is the size of the problem. So few pages there, many pages there. The first algorithm is a straight line because there's a one-to-one relationship between how many times you turn the page. Second algorithm is still a straight line, but its slope, if there's n pages, would be n divided by 2 instead, because you can do 2 pages at a time instead of 1. But the third algorithm, and where we spend our time in a course on computer science, is how do you write code? How do you solve problems such that the curve looks like this? Logarithmic, if you recall the phrase, but it's a fundamentally different shape. And it means that the time involved to solve your problem grows so much more slowly than those other algorithms instead. Now, besides these ideas, which we then in a class like CS50 and computer science more generally use to start solving real-world problems in data by writing code and other mechanisms, CS50 itself is very much a community with traditions, whereby we start the semester with CS50 Puzzle Day, an opportunity to get together without needing any CS background and solve some interesting puzzles collaboratively with friends. Lunches every Friday to make a big class otherwise feel small. A CS50 hackathon from 7 p.m. to 7 a.m. in healthy times at the end of the semester, an opportunity to create your very own final project, and then a CS50 fair, campus-wide exhibition of all students' final projects. And these are all traditions that unfortunately have been on hold for quite some time. But we thought we would paint a picture here in closing of a 2-minute video that the team put together that first tells the tale of what times were like just in fall 2020, not too long ago on Zoom, to fall 2021, whereby we were all here together but masked and not quite gathering in the same frequency as we might otherwise do. But now, ultimately this year, do we hope we'll see a much more normal, much more traditional fall to which you are all cordially invited. So this then was just a taste of the intellectual enterprises of computer science and the art of programming. And this is CS50.
Those days are done, but I still glow. Oh.